Jake, you should
Okay,
be.
here we go.
Okay, cool.
Okay, cool. You're able to get it figured out.
Well, it works now. Donnie, I already
Okay.
figured it out, but you and your highly.
I thought.
I'm renaming you to a dictator again because I wasn't allowed to record. Anyway, okay. So just to recap, the part that was not recorded, we have to pick an airfoil, but the airfoil really only determines what the CL and CD of the wing will be. You figure out the rest of the wing characteristics from your performance analysis, and then you just apply the airfoil to that wing. And so hopefully from performance, you are supposed to come up with either a CL that you wanted or at least the things needed to get that CL. So that would be using the lift equation that I will now pull up for inconvenience. Okay, let's see, where's the button? There we go. So it's not showing me the green border, but this is the lift equation page, right? Anyone? Page, is it showing the lift equation? No? What is it showing? I can't tell. Oh, there we go.
Like showing your assignments right now.
How about now?
There we go.
Okay, fixed. So we know how much lift we want because in steady level, we want our lift to equal our weight. And so that's why if you know your weight, then you're on the right track. So hopefully you guys figured that out. And then these other numbers are other things that we can either assume or want to have figured out by doing performance. So rho is the air density. We can just assume that's 1.225 for now. And we can improve that assumption using like weather data and stuff later. And then A is the wing area or a reference area, but that's another thing that we hopefully figured out during performance. And then V, it's V squared in here, which is why velocity has a major impact on lift, but that's going to be our cruise speed because we want to design to the cruise condition and then just make sure that, or for a plane like this, we want to design for cruise condition and then make sure that at the limits of our flight conditions, like at stall and stuff, that we're still meeting the requirements we have for that. But since we're not like a fighter or something that needs to be flying around at stall, we don't necessarily need a design for that condition from the beginning, at least. So yeah, so hopefully from performance, we have a weight, a cruise speed, and an area. And Laird told me that you guys either have that information or have what you need to get that information. So can somebody verify, validate one of those two things put together that you have that? Because if not, he said I could give you hints about how to find it from the stuff you already have, but you got, that's like step number one. So any of the four of you that are here.
In the doc, I'm seeing that we found a wing area.
Okay, that's good. That's one of three.
Yeah.
We have a weight.
Okay,
yeah, we have
three.
weight.
Nice.
Did we figure out the wing shape yet?
That's not, well, okay, so it depends what you mean by shape. If you mean airfoil, that's why we're here. If you mean plan form, then that's a little bit up to you guys, and it's not necessarily dependent on the airfoil or the area because the shape more determines your flight characteristics than your like absolute performance.
Okay, I must have been confused because when you said airfoil, I thought you were referring both the planiform and the cross section of the wing. So that's why I went in here. But where should I go for like the planiform? Would that be Laird's group?
Maybe. They are talking about configuration, so I don't know if they're going to include like planform design in there. But I did talk about that a couple meetings ago, which hopefully was recorded, but I can check that in a second. Probably DBF something. They're supposed to be recordings of the.
Well, don't worry about pulling them up. I can just head over to Laird's group.
I just want to see if it's already in there. Okay, yeah. So I think in this YouTube video was the one where we talked specifically about Where's the chat? It says it opened, but I don't see it.
Is that the one where you were on Wikipedia?
Yeah. So that
Oh,
was like,
I attended that meeting, so I remember that.
yeah. If you want to review that, it's in there. The Wikipedia page also exists, obviously. But like, I don't think we are planning to like guide you guys through that part of the design because it's a little bit arbitrary. I mean, like the default is a rectangular wing, and then anything you do other than that would just be because you want it to handle a certain way. You could go talk to the people in the other room and see if they're gonna like cover that, but my guess is they're not. But yeah, airfoil specifically is just the cross-sectional shape of the wing.
Okay, so that's my bad with definitions. Sorry
No
about that.
worries.
I'll go ahead. I'll go check out Laird's room.
All right, have fun.
Good luck, guys.
Okay, so
I don't think we have the coefficient of lift, but can we calculate that?
yeah,
Using
so
weight over
yes.
pressure.
Also, in case no one remembers, this rho v squared over 2 or 1/2 rho v squared term is the dynamic pressure.
Oh, that's okay.
And so you can just write that as Q, and then when you're solving this, it's easier to just use Q instead of dumb fractional inverting things. So yeah, CL is L over QA, or L over 1/2 rho v squared A. Also, this A might be shown as an S sometimes because aero people use S as area for some reason on occasion. I think it was from like back in the good old days when everything used to be written as like integrals, then the integral of the like wing shape over the length or whatever was an integral, and so they shortened it to just the integral symbol and then it became an S or whatever. But anyway, so S or A will be area, and then yeah, so that's how you would find your CL. And I don't think I heard anyone confirm that you guys have a cruise speed, but I can guide you on how to figure that out from the stuff you already have if you don't yet. But if you do, then just use that.
I don't think we have a cruise speed.
Yeah, we haven't calculated that yet. Okay, so according to Laird, you guys should have a function called lapcalc parabolic wind. Is that a thing? Okay, so if you, let's see, what did he say? Apparently, if you run that with everything you have, he didn't say exactly what to plug into it, but it should spit out a number called vtop, and that is your theoretical max speed according to that function, I suppose. And you can use that as your cruise speed for now, at least. That's a place you can start. So if anyone wants to try that, go ahead. We'll do that right now. Cool. I will, while you're working on that, I'll cover a little more like of the theory of airfoil selection, I guess. I gotta try and find my my function that I used for this, because it's gonna be really hard to explain if I can't show you guys what I'm talking about. Okay, very good. Okay, hopefully this runs. It's going to take a little while, so that should give you guys some time. I have a pretty solid computer. Let me check. It's a little busy right now, but it takes a solid minute and a half plus to run this like airfoil iterative calc code. So there's a lot of data going on there. But once it spits out its like images and stuff, then I can pretty easily explain what it's doing. And once you get those speeds, go ahead and try to find a CL based on them, and just let me know what you guys are getting, and I can verify that it's not like about to waste a bunch of your time. It's quite annoying that sometimes the little green border thing doesn't show up in the Zoom share, so it's hard to keep track of what is sharing.
For the power in the dock, is that the power loading?
Can't tell you.
Which I think we have both on there, don't we?
Other units.
The power one. The power looks empty, unless. And do you know what the power is?
Let me see. I mean, if we have power loading, then we have the power, but power loading. Let's see. 29 times. Actual is like 243 watts, but with the efficiency thing, it's like 487.
Okay, so we'd use 487.
So this thing really just aired out on me at some point, but I don't know what it was doing, but I got some data anyway, so I don't really care anymore. And there's a step you guys won't really be able to see because I instead of making new plots, I just modified the old plots, but hopefully it will not be too difficult to follow along.
Okay, I have a B top. I don't know if it is reasonable, but there's a number. It's 74.832. I can figure out what the units are though.
What are the units on that?
That's what I'm trying to figure out right now. Feet per second.
Like 74 feet per second.
74 point.
Oh, 17.
74.832.
What was that? Speed again.
74.832 feet per second.
All right, that's a pretty good range to be in. So pop that into this equation solved for CL. What's your weight again?
8 pounds.
Okay, yeah, pop that in here. Make sure your units are consistent and stuff. And then that'll, if your units are correct, then they should all cancel out and CL should be unitless.
You said we should use 1.225 per row.
Say again?
You said we should use 1.225 per row.
Yeah.
Okay.
But that's in kilograms per meter cubed, I think. So that's a good, like, that's like the ISA value for density at sea level, but it's in the wrong units if you're using pounds and stuff. So you can either convert all your other stuff to metric, or you got to convert that to imperial, which tragically I think means it's like slugs per cubic foot or something gross like that. So Blue Cash.
Hey, sorry I'm here so late. I had an assignment that ran really long.
I feel that.
What are you guys up to?
Trying to choose airfoils, which is an arduous task.
Okay.
Does 0.0103 sound small?
What units did you try to use?
Imperial.
So you got your velocity as how many meters per second?
No, I used the
whoops.
system, the
Imperial is
74.832.
So then what was your density?
Density ended up being 0.07647 pounds per foot cube.
So remember how I said you got to use slugs? It's because pounds are not a unit of mass. It's terrible. Nobody likes it. Slugs are the worst part of the imperial system by far.
Okay, I got 0.33 this time.
That sounds quite reasonable. If anyone else is working on it, continue, because it would be good to have a couple verifications. And so from there, that number is the number that we want whatever airfoil we pick to generate, if possible, at 0 alpha. So let's see, I don't know if I talked about this in the past, but an airfoil that has no camber will create 0 lift at 0 alpha. So if the airflow is going directly from left to right, like horizontally over this airfoil, it won't generate any lift, but it will still generate drag. But if it's going over this airfoil, still the exact same flow direction, so 0 alpha, this will generate lift and drag. And the reason it generates lift is it has what we call positive camber, where the camber line is above the chord line, and the chord line is directly from the leading edge to the trailing edge. So on this diagram, it's like this black horizontal line. The camber line is the sloped greenish one, and it's roughly approximating the midway point between the two surfaces, the top and bottom surface. It's in some airfoils, I think for this one potentially, it is literally just the halfway point, but it's not always that, because you can have the camber line be like outside the airfoil, or I don't know, that might be wrong, but you can have some really weird camber lines, and they basically determine how curved and where the airfoil is. And the reason they generate lift at 0 alpha is the one we had before can generate lift at cannot generate lift at 0 alpha, because all the air going over the top goes the same speed as the air going over the bottom. And so there's no pressure difference until you give the, here, let me do this. Just slide that over there. Okay. Can everybody see the screenshot of the thing? Okay, cool. So now, if I don't think I can rotate the whole thing, can I? That would be great. No, but anyway, so I'm just going to draw the flow direction, because that's easier. So if the air is like this, then it's like hitting more on the bottom than it is on the top. This is pretty intuitive, so I'm not like, if this seems like it makes a lot of sense, then that's a good thing. And so there's a higher amount of pressure on the top than there is on the bottom, and that means there's a pressure gradient, and the pressure gradient creates a lifting force like that way, roughly. It also creates drag because the actual force is like kind of like this, and so the lifting force is, we always describe lift as the force directly perpendicular to the chord line, and the drag as the part parallel to the chord line. That's a general rule. If you are in like aero classes, you'll learn it more rigorously than that. But the problem with this, as you might be able to see, is that if we want a lot of lift, then we need a lot of angle. And eventually there's a point where, like, if you put the air like this, then the plane's not really flying, because this doesn't mean, like, this means the air, which you're generating from going forwards, is now coming from like the bottom of the airfoil, and you can't really fly that way because like this is the forward direction. This is not the forward direction because remember, we're like tilting the wing, not tilting the wind. We're always assuming the wind is coming from the front. I just can't rotate the picture to show that. So you're basically only generating drag, and you can actually see this point where it changes over, and that's the highest, the point of like the most lift you can get out of it. And what angle that's at is in this chart here, which is CL on the left side, positive and negative, because you can imagine if you tilted it the other way, so that like you tilted it down so that the wind was like forward is coming, the wind's coming from this direction, then you would have more pressure on the top than on the bottom, and you could get lift downward or negative lift. But so at 0, we have 0 lift, and then the highest we can get at a speed that gives us like a rounds of 1,000, I mean 1,000,000, would be like 15 degrees. So if we were to tilt this like 15 degrees into the wind, that's the most lift we could possibly get before, if we tilt it any farther, it starts to drop back off, and then we get stall, because then the so like at 15 degrees, there's enough air still getting around to the back that it stays pretty much attached the whole way down, and we get enough lift out of it. But then if we start to increase this even more, the flow doesn't stay attached very long on the back, so it might get to like here, and then it starts to detach off this way, and all of this area doesn't generate lift anymore. It's just like wasted energy because there's vortices that develop in here, and the flow is separated, and that's how you know you're stalled. And you don't generate, like your lift goes down dramatically when the flow starts to separate. So that's why we can only go so high on the alpha here before it starts to drop off. And the faster you go, aka the higher so these numbers, which I think we talked about the Reynolds number, but the higher the Reynolds number, generally, if you keep the wing the same, then it means that you're going faster, because the Reynolds number depends on the size of the wing, the density of the fluid, the viscosity of the fluid, and the speed of the flow. So if we keep all that other stuff the same, then the faster you go, the higher the Reynolds will be. And so you could imagine if we're going really slow, then the flow might detach easier, because it's not like, I don't know, I feel like an analogy would be best for this, but I can't think of one super easily. But like, it just doesn't have as much inertia, I think is the right way to put it, like keeping it attached. And so it detaches earlier, and that's why you can't reach as high of an alpha at a slower speed. And therefore you won't get as much lift, but at a higher speed, you can reach a higher alpha as the flow stays attached longer. But that's all just for uncambered airfoils, where again, at 0 alpha, the flow like this, pressure on the top and the bottom is the same. If we have camber, so now, hopefully it keeps me on the screen this time, please, thank you. Now, even at 0 alpha, when the flow reaches the leading edge, it's gonna split, and I'm just getting this down a little. So the flow going down here has to move, and the flow going up here also has to move. But you can kind of, I don't know if any of you have ever heard like, oh, the flow has to get back, they both have to get back to here at the same time, so this one has to go faster. That's dumb and not real, and there's nothing that makes the flow over the top and the bottom have to reach here at the same point. The easiest way to like make it intuitive is just that the flow on the top is getting pushed out of the way more, and so it's like if you want to displace something a farther distance, like from here to here, it would have, if there was no airfoil, they would both just be here. But on the bottom, it has to get displaced from here to here. But on the top, it has to get displaced all the way up to here. And so since you're the one moving through it, you're like pushing it out of the way, and to push it this far over this same distance, it has to go a lot faster. So what you just need to like accept out of that, even if it's not super easy to understand, is that the flow over the top goes faster than the flow over the bottom. So if these arrows are the same amount of time, it might be like that. Now, what's cool about making flow go faster is that because of the Venturi effect, which is like, if you don't remember what that is, if you have a Venturi, which is like this throat thing, then, oh God, drawing is hard. Then as the flow comes through here, it'll speed up. And what your boy Bernoulli noticed is that as it speeds up, I can draw that like, man, I have a new idea. This is gonna be great. I can, if I put it on this screen, then I can draw with the pencil, and that's way better. So let me just mute all my shenanigans first, because they're gonna become bothersome. Okay. So now, there we go. There we go. Okay, so if we have like small arrows equals slow flow, and then as it starts to get in here, it goes really fast. Because the mass flow rate is staying the same here as in here, but the area is going down, so the flow has to accelerate. What Bernoulli noticed is as the flow speeds up, the pressure here is like low, but the pressure here is like really high. Wait, sorry, that's the opposite of what I meant to say. The pressure here is higher, and then as the flow speeds up, the pressure goes down. That's correct. That's the low speed version of like the incompressible version of conservation of mass is the Bernoulli equation, which says this, and it doesn't apply to compressible flow, but we don't have that anyway, so don't have to worry about it. You'll learn about it in aero classes if you need to. And so what we get is as the speed is going faster up here, and you can even see this in the, like if you ever look at CFD for an airfoil, there's like a huge low pressure region here, because if you think about it, it has to go from here to here, but most of it, like most of where it's being forced into like a large distance is right in the very beginning, and then it's not forced that much farther up over the remaining distance. And so there's a huge, sometimes even like negative pressure spike, not negative absolute, but like, yeah, the pressure goes down a lot up here, and then it stays low like all the way back to here, and then somewhere around here it'll become like the same as it is all along the bottom, which is positive. But so that means that for this whole area you get a low pressure, and this area you get a high pressure, and that pressure difference causes this lift force. So that's how, even if you have no, give me my thingy back, no angle of attack, you still get lift out of this airfoil. If you do have angle of attack, then it becomes both. You get lift from the speed difference over the top and bottom, which that is probably a thing on zero camber airfoils also. I would guess that speed, the flow speed around each side plays a part anyway, but you don't even, I mean, like for a flat plate, you can basically assume, like if your airfoil looks like this, then you can get lift out of it by pushing air at it at an angle, which is why your hand makes lift. I mean, your hand's not an airfoil, that's somewhat similar to a flat plate. You can't really, this is like such a sharp edge that you shouldn't really expect any flow to attach back here, but so it's going to separate like this and like that, but just because you're like, so this is going to be low pressure by default because all the flow is separated there, and because you're pushing air against this, it's going to be high pressure, so you can still get lift out of this at an angle of attack. It's just much less efficient than even a zero camber airfoil, and doesn't generate any lift compared to a cambered airfoil at zero AOA. So anyway, the downside to all of this cool stuff is that every time we generate lift, we automatically generate drag, which I think I talked about in configuration, because if we look at the wing, like from the back, which is going to be kind of weird. So like this is the airfoil, here's the wing. Sorry, that's the fuselage. The airfoil is like one little slice of this. And it's doing its thing the whole way down. So this whole area is low pressure. Or our small area is low pressure. That's fine. And this whole area is high pressure. Then pressure always wants to like equalize so that everything's the same pressure, right? And the wing can't go on forever. So that means that at the end of the wing, the high pressure tries to move around the wing and equalize with the low pressure. And as you're moving, different view now, try to keep the colors going. As the wing moves forwards through the air, then it's continuously trying to curl around and it makes this spiraling vortex thing. And that's what a wingtip vortex is. And you will create one of those anytime you're generating lift. And that's lost energy. And it's like adding energy into the air that's not creating lift for you. And so it's creating drag. And that's the main part of induced drag. There might be, like, I'm not positive on this, but I think this also generates a downwash behind the wing, which might have something to do with induced drag. But like the easiest part for me to think of it is the vortex, and that it goes well with like if you make, remember when we were talking about aspect ratio, if you make your wings super long, then your aspect ratio goes up a lot. So like you have a really long skinny wing like this. Don't build this wing, it would break. But if you do this, if you think about where the lift is, because like if you just made a really long wing but it was still really thick, so your aspect ratio is still low, then a lot of the lift is still down here. But if you do this, then only like a tiny bit of the lift is actually near the tip for any given wing. And so there's a lot less of the pressure that's able to like loop around to the from the end. All this pressure that wants to equalize would have to go a lot farther. And so in general, the high aspect ratio wing is a lot more efficient than the low aspect ratio wing, where basically like all of this pressure has really easy access to the wingtip and can go around and make a big vortex. And that's why when we made the super low aspect ratio wing a couple years ago, we had to add like fences onto the end specifically to try and reduce the vortices because they were so huge and adding a ton of drag. And that's what winglets are for also on like airliners, is they block this thing and make the vortex smaller. So anyway.
Wait, how did you know that the vortices were huge?
Well, so like our analytical model was just like, yo, you got some fat drag there, dog, because you can kind of guess your induced drag based on your wing characteristics. And like there are reasonable values, and those values are based on wings that are roughly, I'm hitting the edge of stuff, but wings that are roughly kind of this size. And so when your wing has like the same area, but it's like this, then you just have a ton more wingtip relative to your chord. I mean, your span, oops. And so like this whole thing can be generating a vortex, whereas here, like it's only this, and on this tiny wing, it's only this tiny bit. And that was validated by like, it didn't want to go fast basically when it didn't have any fences on it. And the fences also helped with directional control, but that was a slightly different problem. But anyway, so yeah, so hopefully that makes everyone understand why we want to make lift and avoid drag, and why a cambered airfoil is helpful. Oh, I think I didn't quite get to the end of the drag thing. So the greater, and it's hard to keep track of what I'm talking about, but yeah, so you can kind of think of lift being generated by those two mechanisms of like the flat plate generates lift, therefore basically pushing on something, or Newton's third law, must generate some lift. But Bernoulli's thing of like the flow speeds and the pressures and stuff must also generate some lift, because we have zero angle of attack and yet we're still generating lift. So if you keep both of those in mind, that can help you start to figure out why, oh, I literally can't go back any farther. Why we need to like balance these two things. So, and why we want an airfoil that gives us our desired CL without any angle of attack. Because if we do that, then we're not adding any drag from like the Newton approach, while still getting just enough. Like we don't want extra CL necessarily, because that will inevitably come with more drag. So we want the airfoil that gives us just enough lift while giving us as little drag as possible. And to do that, we want to be flying at 0 angle of attack. Okay, I think that covers the important like baselines or fundamentals or whatever. So one way to go about that is just look at every airfoil and be like, hey, at 0 alpha, what CL do you get? This one is like 0.5 roughly. Compared to this one, because it has no camber, is at 0. So instead of doing that, which takes forever, and there might be airfoils you just don't think of that you can't then check. What we did for competition was we wrote some code, and I will show the code quickly. And the code uses AVL, which we haven't gotten into, but if you just imagine, like, if I could run this same thing, that for any airfoil, I plug in a bunch of I basically say, here's either a CL I want to fly at or an alpha I want to fly at. What, because I know basically I want to fly at 0 alpha and I know the CL that I want to fly at. Then like for this airfoil, what do I get? That's the point of the code. And that's why at first I said for a whole bunch of alphas and a whole bunch of airfoils, what will give me the CL I want? But then I realized it was kind of easier to be like, for this CL and a whole bunch of alphas, and a whole bunch of airfoils, then what do I want? But so instead of doing like the basic version, which is just for the airfoil, AVL lets you do it for a whole plane. And so we're plugging basically the plane into this, that's all this stuff. And then here I go, okay, here's a whole bunch of, oh yeah, these airfoils all have 4 digits because they're literally defined by those 4 digits. So if we look on here, the M, the P, and the double X, that's what defines the shape of the camber line and the thickness of the airfoil. And so that's why the 0012 has no camber, so 0 camber amount, can't put it anywhere, and a thickness of 12. The 4412 has 4% camber at 40% of the chord and a 12% thickness. And you can generate any airfoil by just filling in numbers here. And that was basically the approach, because there's other series of airfoils and others that aren't in an ACA series, but this was like starter mode. We didn't get past starter mode, but it's an approach. So I was like, for all the possible camber amounts and all the possible camber positions and all the possible thicknesses, which ended up not mattering because thickness mostly affects your viscous drag and AVL doesn't model that very well. Then just iterate through all of those. So every possible camber and camber position, and then figure out what the, like for a set CL, give me a bunch of alpha values that will give me that CL for each airfoil, and then show me them. So when it shows me them, it looks like this. And there's 2 of these like curved plot things because we knew like our 2 different CL values for the 2 missions. But this like level plane is alpha equals 0, which is where we want to cruise if possible. And then these like colored lines are the intersections between, or like as close as possible, because you can't have like a camber of 4.5, it has to be 4 or 5. So it's the closest possible airfoils to this curve on the plane. So basically the blue line is the set of airfoils that will give us an alpha of 0 for the CL we want for this, like this CL curve thingy, surface, I guess. And the red line is the set of airfoils that will give us an alpha of 0 at this CL for that surface. And then you take it over to drag. So this is only looking at CL and like which airfoils give us the desired CL for a bunch of alphas, and then find the one for 0. And then we need to see, okay, well, out of those airfoils, which ones will give us the least drag, because we want the lowest possible drag. So this surface is for every airfoil, what CD will it give you at, I think, 0 alpha, because you want like to fly at 0 alpha. And then the lines are literally just transposed over from this curve to this curve. So if you look from the top, like they're actually the same lines like that. You can't see the red one because it's underneath the surfaces, but so those lines are the same. And so if you just look basically along the line, like where is the lowest drag point, if you project that line down onto the surface, and it turns out it's at these points where you have 0 camber, because of course it is. And I don't remember why that actually worked for us, because oh yeah, so the reason we ended up going with the 0 camber airfoil, if I remember correctly, I'm pretty sure we did, or like maybe it's at 1 and not 0. Oh yeah, so the camber amount is at 1 because you can't put it at 0, you don't get any lift. But basically you can't, there's no, what the fact that these surfaces never intersects tells you that you can't have an airfoil that will give you 0 CL, 0 alpha and fly at both CLs, because they're mutually exclusive like that. So we were like, okay, well, we should just pick one in between. And then eventually it ended up not mattering because we realized we could fly both missions at the same weight, which means the same CL, which means only one airfoil. And we ended up picking this one, I think. But that was the process to try and figure out an airfoil, because again, you know your CL, you want to fly at 0 alpha for the least added drag, and then they're going to have some induced drag. So which one that works for your CL flying at 0 alpha will give you the least drag. It turned out to be these ones. I don't think it makes sense for you guys to do this whole process for mock comp, but it's still a good thing to understand, because like it illustrates the idea behind choosing an airfoil. But this took a long time to figure out. So if you feel like this is like not a good approach, then I probably agree with you for mock comp at least. So yeah, so what I do think would be a better approach is look around at some different ones, maybe try and pick up on some of the trends from this, which are that, like, remember that drag is the vertical axis here. So if you have a camber of 90% and you put it at 90% of the way down, we can draw that actually. Hopefully it might not let me, but we can try. Then it's gonna look like this, and that might not be a great airfoil. So, you could try it, but according to AVL, it's a lot of drag and not a lot of lift, as we can see here. A lot of, or let's see, yeah, a lot of negative lift actually. I don't know, I forget how to read my own graph, but anyway, that's airfoils for you. They're kind of annoying. The fact that there's even more than one series to choose from is like a terrible idea in my opinion. I think we should just lock it down to 4 series only. But you're also welcome to look at like 5 and 6 series. If you want to know what 5 series, like how it works. I think it's mostly the same. So it's like, yeah, like in 5 series, you just pick your camber by saying like, yeah, I want my lift coefficient to be this, multiply that by 3/20, and then that number goes in L. Great system, I know. So then position divided by 20, more random stuff, normal versus reflex camber. I barely even remember what that means, and then thickness again. So it only gets more complicated from here, but go ahead and have fun. If you have questions or want to see more data or something, then you can go ahead with that. And I was going to also do tails today, but if you guys actually want to make any progress towards like choosing an airfoil, then we probably don't have time for that. So I'm fine with you guys just working on airfoils for the rest of the time or until you have to leave or whatever. But if you would rather do that another time, like if you guys are meeting by yourselves or something, no idea what you guys are doing on that, but I can go into tails because it's not as complicated or long to figure out, at least at a basic level. So that's an option, but I'll leave it up to you guys.
Jake, do you mean like airfoil selection for tails, or do you mean like tail configurations and tail
When I
colors?
just said tails, I meant like tail sizing / stability.
Hmm.
Because
Okay.
if you want to choose an airfoil for a tail, just choose a zero camber airfoil. Boom,
Sure.
done.
Sure.
Fun, quick, aero tech tip, aero quick tip, something.
Do you have any thoughts? I mean, I don't want to hijack your session or whatever, but we were wanting to like wrap up our configuration selection, and I don't know if we have a whole lot of stuff to say about like what kind of tail, like V-tail versus T-tail, whether you should have like a vertical and then a horizontal on top of the vertical, jazz like that. I don't know if anyone else has opinions they wanted to shout out into. Maybe that's totally off topic. Maybe I'll shut up.
I mean, as long as they're putting some kind of rationale into their choices, then that's probably the only thing of significance. The sizing can affect the like what you should be doing for configuration at the extremes, because like if you realize you need a super big vertical, then you're probably better off making 2 verticals and so doing one of the twin configurations. Otherwise you have to build a really fat vertical to support itself.
Sure.
But I mean, that's not to be expected. But like any of the things that I talked about before about like why you would do that kind of tail, even if it's like, oh, we want extra stability, but we don't have a reason to need extra stability, we just want it, like that's probably allowable. So
Sure.
I'm not
Okay.
yeah,
Low key on tails. It'll
Yeah.
fly probably. Okay. Sure.
like a T-tail basically is only more, like the purpose of a T-tail is it's just slightly more efficient. The downside of a T-tail is it sucks if you stall. So if you think you're never ever going to stall, then maybe you could go with a T-tail. But if you don't even need the extra efficiency, then it probably doesn't matter.
Sure.
It's just
Okay.
more, it just gets the horizontal tail out of the downwash of the wing.
Right.
Which, according to all the planes that don't have T-tails, isn't a big deal, but some do. So yeah,
Okay.
it's like if you look at planes that do have T-tails, a lot of them are like business jets or things in that market. And my guess is because they can get like another 12 miles or something of range to tack onto their marketing number if they make it a T-tail, and they can't if they make it a normal tail.
When you're saying T-tail, is that this guy and
Yeah.
then this guy is something else? What's this guy?
That one's a normal tail.
No. Okay, cool.
Well,
Great.
I mean, like the if you put it halfway between the fuselage, like the horizontal is not on the fuselage, it's like partway up the tail, then it's technically cruciform, but that's just a weak version of a T-tail. So go big or go home.
Okay.
And T-tail just, yeah, it means the elevator. I mean, the horizontal's
Sure.
mounted on top of the vertical.
Awesome. Awesome.
But you could also do literally anything else if you can justify it. And because it's mock comp, you don't actually have to like score or justify it. You just have to explain the benefit of it, basically.
Sure.
Also,
Thanks,
I think a different Jack, not the one that's here now, but the one that was here earlier, thought I was going to talk about plan form design. Did you guys talk about that in configuration or what?
What are these words?
The shape of the wings when you look at them from the top.
I don't think we've ever designed that. I don't know shit about that. So no, we did not talk about that.
Yeah, I mean, our wings tend to always literally be rectangles, and if they weren't rectangles, then we would have designed them to be something else. So it sounds
Sure.
correct.
I think usually our rectangle wings are just manufacturing. I don't know. Can we do like a changing cross section on like the foam cutter?
Sometimes.
Technically, yes. It's a little confusing on how you set it up, but I
It
think
also
it's
has
much.
limits.
Yeah, it did. The foam cutter has limits, but I think it's much simpler now that we have a laser cutter
Yeah.
on hand in the lab. We can do change variable, not variable, but a changing plan form area for the wing.
Yeah, I guess.
Yeah, I mean, there are, I don't know how many of the people here, including vets or non-vets, were like listening in the wing design, configuration, whatever discussion, because that's where I talked about the plan form stuff. But most of the variations are either for supersonic flight, aka unnecessary, or better handling, which we usually don't have a problem with, so also unnecessary. But it doesn't factor into like the rest of your performance design. It's mostly just about changing your handling characteristics.
Did you
And
record that, or do you have it
yeah,
documented?
it's on the YouTube. I found it earlier when Jack was asking about it. But
Okay.
so there's not a lot of reasons that we would change it. But as far as manufacturing, there's like some options that mean variable cross section and some options that just mean the same cross section but in a different, like pointing in a different direction or something. Because like if like a swept wing, the simplest form of a swept wing is literally just like it's like a normal wing but mounted at an angle instead of mounted perpendicular. So some of them might be somewhat manufacturable, especially like with the laser cutter. They're easier to replicate at least. And then what I'm pretty sure because I think I've heard it before, but I think the foam cutter just has like a maximum draft angle, and whatever that angle is, that's the maximum angle of whatever that we can make. So like the maximum taper angle or sweep angle or whatever. To some extent, because I mean, you can also like a lot of the parts are they have a very consistent angular difference from a normal rectangular wing. So you could like cut a swept wing perpendicular to the wire on the foam cutter. So the foam cutter's not even doing anything different. And then you just cut the ends off at like an angle with the hand bow or a saw or something. And boom, you got yourself a swept wing. So yeah, they're varying degrees of doable, but I don't think it's necessary to like hard limit them on manufacturing stuff that seems plausible, since they don't have to build it anyway. But
no, they're building it.
They're
Stop
building it.
Saying that.
Oh yeah,
since
they have to build it anyway, we should tell them that they must build a conventional, normal everything. But
no, I think we should definitely experiment with our manufacturing methods.
There just aren't that many good reasons to change it in the first place. So yeah.
Our planes always look the same. And I think even if it's not necessary, trying something new would allow it. We'd be like, yeah, we know how to do that if it were to actually become like relevant or helpful later. So I'm totally down for experimentation.
Yeah, I mean, maybe there will be maybe one day they'll change the lap requirement so that like you have to do a full power off stall halfway through a lap or something, and then all of a sudden everyone will be building like taper wings and they'll be like, oh my god, this is harder than I thought. So you never know. Or actually potentially more plausible, maybe they'll make like a landing distance requirement or something, and you have to like come in super slow so you can land in like 5 feet or whatever, and then it'll be important to like fly safely near stall instead of like the problem with our rectangular wings is if you stall them and like you're near the ground, so you actually need directional control, you kind of won't have it because the ailerons stop working because they stall before the route, and that's the whole point of taper, is to like avoid that. So It is actually useful in some cases, just not any of the cases that we've ever needed to build for so far.
Interesting.
Yeah.
Such knowledge. Good job,
You know, if only it converted into grids, that would be great.
Jake.
That's
What
part.
was the what
I
was the
feel-
name of the what was the name of the code you used to get the data on the airfoils?
I wrote it,
You wrote
and
it.
then I didn't put it anywhere. So
Okay.
actually, I might have put it somewhere in the Dropbox because I think Laird asked for it. So I can look for it. Hold on.
Okay.
I will. I'll see if it's in there somewhere. But I never. Whoops! I never intended to publish it. So all the from what I've seen of like the other code tools that you guys have been using, they were written by very smart and comment-heavy people, and you should not expect that level of interoperability. Plus, it runs on AVL, so if you, well, like the platform is MATLAB, but it requires AVL to do the calculations. So if you actually want to run it, you're going to have to like figure out AVL and make yourself a model and stuff, which I was probably going to talk about at some point, but we have not done yet.
Okay.
So best of luck. But I mean, it's a good tool. So if you just want to learn it on your own, have fun. It's pretty nice.
Do we usually do AVL during a mock-com setting?
No,
Or is it
I don't think we ever have.
Uh-huh.
I mean, otherwise I would have learned it prior to last fall.
Well, sure. Yeah. Maybe that'll be reserved for if you're taking on it. You're taking on a successor in the fall or over the summer or something.
Yeah.
Um,
Let's see. Where would I even have put that? Oh, I found it. Okay, so in the DBF Dropbox, in the 2021 folder, in the performance folder, there is 2 copies of AF design, one of which is clearly identifiable as Laird's due to it being labeled AF design poop.m. It's a shade on Laird. So you can try either of them. I don't know what he changed about his, but mine is probably essentially the same thing I was running. And then all the other files you need to actually run it should be in there. It's got avl.exe, which is AVL itself, and then it's got the .avl.mass and .run files, which are how it actually, that's all data that it needs to execute. So I have a reasonably good feeling. I wouldn't run it in the Dropbox because it's probably going to make and delete a bunch of files and stuff, and Dropbox hates it when you do stuff like that. So if you want to run it, I would copy it like onto your computer and then run it locally. And you can try your best, but you're just going to be running it with like the plane that's already in there, unless you figure out AVL and how to change the plane model and stuff, which it takes a while to learn. It's like, there's like some tutorials on YouTube and stuff that you're welcome to do, but they're each like half an hour long, and you have to watch them like a lot of times to actually get all the data. Like if you try to follow along in real time, you'll be on like step 4 out of like a billion by the time they're done. So yeah. So based on the fact that 15 minutes have elapsed and no one said they wanted to hear about tail design, I'm gonna leave it for Thursday or whenever. You guys are, like I said, welcome to get going or take a crack or whatever phrase you want to use on airfoils. I will be here to answer questions either until 8 or until I get dragged to the eating zone. But that's pretty much, like, that was already the only stuff I had to inform you about on airfoils. If it seems like choosing one is kind of impossible, then good job, you figured it out. But yeah, I hope you have fun. I hope this doesn't make you quit. And best of luck. I'm gonna stop the recording there because otherwise it's probably gonna be like another half hour of silence, but yeah, GG.
Thank you, Jake.